Why is that light bulb rotating? It seems like it's the natural way for it to spin. If we look at it, it's a solid object, and as I rotate like this, for a complete rotation, a point on the outside has to travel one of these big circumferences. But a point on this end, for one rotation, only has to travel one of these little circumferences. Assuming it takes, I don't know, half a second to do one complete rotation, this point traveled more distance than the other. And since velocity is just distance divided by time, that means that this part was going faster. So I thought it might help to show the math behind that claim. Again, if velocity is just distance over time, the outside covered the most meters in the time it took for a rotation. So that's the most meters per second. And that means the outside was going faster. The fat part goes faster, the skinny part goes slower. And that's what makes a turn. What I just described is linear velocity, the thing we've been studying up till now. But in a different way, every point on this bulb has the same speed, because it rotates the same number of times, or the same angle, in a second. There's nothing here that's rotating more degrees per second than anything else. So here's that argument in equation form. We could say everything went the same speed because delta theta, the change in angle over the change in time, was constant. So we're really talking about two different kinds of speeds. Linear velocity, what we were looking at before, is how fast do we cover distance. Angular velocity is how fast do we cover angle. This is our introduction to things that rotate. And we're going to see that things that rotate are simple to understand using the same concepts we've learned already. Things like energy, momentum, forces, motion. As long as we can replace the idea of distance with the idea of angle. We've already seen that velocity goes from distance per time into angle per time. And all these other concepts will have similar changes. Angle can be measured in a lot of different ways. I've got here listed that we measure it in degrees, which is what we've done up till now. But I think you've also used the unit radian in math class. In the former Soviet sphere of influence, they use another unit called the gradient, which is like degrees, but there's 400 of them. And the rotation is also a measure of angle. Rotations per minute is a really common angular speed unit, and you think of one rotation being 360 degrees. So obviously linear and rotational motion are linked, and let's look at it for velocity. It makes sense that linear velocity, change in distance over change in time, will be proportional to angular velocity, change in angle over change in time. If we spun the bulb faster, we would expect every single point on the outside to go faster. Notice the symbol for angular velocity is a Greek letter, omega. Oftentimes the rotation symbols are in Greek. We also saw from before that the farther you were away from the axis of rotation, the faster you went. So combining these two ideas, we get the equation V equals R omega. The units on that only work out if there's no unit for angle, which seems a little bit strange. But that actually is this when you're using the unit radian, and we need to explain that. So I've got this circle here, and I want you to think of it as a pizza with two possible slices on it. Now, each of these slices has an angle, theta, and a crust length, or arc length, s. And we can see that theta and s are proportional to each other. The bigger the angle at the tip of your pizza slice, the longer the crust. So you actually could use the length of the crust to describe how big a piece of pizza you got. And there's a maximum on how big a piece of pizza you can get. It's the circumference. So to make this into an angle, and to make this valid if we made the pizza bigger or smaller, so we could compare relative sizes of slices, we came up with a ratio. We said that the angle could be expressed not as just the arc length, but as the arc length divided by the radius. How many times bigger or smaller is the crust than the side going towards the center? And that actually ends up being a valid measure for angle, and we call it the radian. This strangeness of having a distance divided by a distance as our definition of angle means that distance actually cancels. And the unit of radian actually is unitless. We put radian in there so we have something to say, but it's just we're measuring angle by how many times bigger is our arc length than our radius. So that's why the angle expression in all those equations just uses the unit 1 for angle. So as I said before, angular velocity and linear velocity are directly linked. The more rotations per minute you spin that light bulb, the faster any point on the outside goes. And this equation V equals R omega works as long as you use meters, seconds, and radians as your relevant units. A similar equation applies for both the relationship between distance and angle. Distance is R times the angle. And also between angular acceleration and regular acceleration. Linear acceleration is R times alpha, whereas alpha is angle per second squared, how fast your spinning is speeding up. These equations are all valid as long as the thing is not slipping. We're going to see that almost every quantity we've studied, distance, velocity, acceleration, but also force, mass, momentum, and energy, have rotational equivalents. So this unit will basically be a review of what we've been doing and extending it to this new type of motion, how things rotate. I just wanted to give an example of how similar the two types of motion are. This is an equation of angle, angular velocity, and angular acceleration for an object that is starting to spin. And you may notice that the equations of each of these functions is really similar to what we've seen already. I know I have this set up with calculus, but don't worry about that if you're not in a calculus-based course. This equation looks just like position versus time for 1D linear motion. This looks just like velocity versus time for 1D linear motion. And there's a third one that we could combine them to come up with as well. So if you're talking about something starting to spin, and starting to spin with a constant acceleration, that's very important, then all the stuff we learned about linear motion works equally well for rotational motion. We're going to see that's the case for a lot of these topics. I have to give some credit for this discussion to Paul Hewitt, who wrote Conceptual Physics. He discussed doing this with a paper cup to the same effect.